Hello all, welcome back to my YouTube channel all about VLSI. Good evening. Hope you're all doing good. So let us start today's session. So we'll start with a topic called Boolean Algebra. Okay, so it is a very important topic in our digital electronics. So before that, before starting our session, if you haven't subscribed to our channel, please do like, share, and subscribe to our channel. Yeah. So let's start today's session. Let me share my screen and let me. Yeah. So in previous session we have completed with the topic called number systems. We have completed the topic called number systems where we have discussed what are all the number systems we have, binary, octal, and how to convert the number systems, and what are all the codes we have, gray code, like that, right? X3 code. Okay. Now in this session we will start with the topic called Boolean algebra. Okay. What is the topic called? Boolean algebra. Basically, Boolean algebra is mathematics of logic. Okay, so I'll write it here. Boolean algebra. We are going to discuss the topic known as Boolean algebra. Basically, it is mathematics of logic. It is one of the most basic tool which is used to analyze and synthesis of which is used in the analysis and synthesis of the logic circuit. So in Boolean algebra, we often have letters like A, B, C, X, Y, Z. We will use some variables, and we also use Boolean values of a variable. And the let's say suppose we can use these variables A, B, X, Y, and we can also have Z. So and the values of these Boolean variables can be 0, which is logic 0, and 1, which is logic 1. So we have these two values which are logic 0 or it can be logic 1. Okay, so these are known as Boolean constants. What is it known as? Boolean constants. Boolean constants. So basically there are two types of levels in Boolean algebra. So these are known as logic levels. I'm going from very scratch level so that everyone can understand. So it may be slow for someone, but it can be new to someone. So I'm going, considering all the people who are listening to this lecture, I'm going from the very basic level. Okay, so we'll go to from very basic level to we will go to some advanced level, high levels. Okay, yeah. Now we have two logic levels in Boolean algebra. One is called as logic 0. One is called as logic 0 level, and another is logic 1 level. So we have two levels. We have two levels in Boolean algebra. One is logic 0 and another is logic 1. One is logic 0 and another is logic 1. So basically logic 0 is used to represent the false condition, and logic 1 is used to represent the true condition. Logic 0 is used to represent the false condition and logic 1 is used to represent the true condition. Okay. Now let's discuss a topic called truth table. So I'm going from very basic level, considering all the type of students who are listening this session. Okay, so someone may feel this some boring, or you have already listened to this, but it may be also new for someone. Okay, so that's why I'm going from very basic level. Okay, now so we'll discuss what is meant by truth table. So basically a truth table represents the relationship between, so it is basically describes the relationship between inputs and possible outputs. Inputs and possible outputs of a logic device or logic circuit. Okay, so basically truth table is a relationship between the inputs and possible outputs of a logic device or a logic circuit. Let's say if we have a logic circuit, let's consider a black box. We don't know what is the circuit design, everything. So that's why it is a black box. Black box is nothing but we don't know what is inside this box. Okay, we don't know the circuit for this. We have some set of inputs to this black box. We have some set of inputs to this black box, and we will get some possible outputs from this black box. Okay, we will get some possible outputs from this black box. So these are the inputs and outputs for our black box. If we supply any particular set of inputs to our black box, we will get some set of outputs from our black box. Okay, and we don't know how this particular signal is being passed, how the outputs is passed, how what is the circuit, everything we don't know. That's why it is a black box. Okay, so to describe this black box behavior, or to describe the relationship, to describe the relationship between output and input of this black box, we use a table called truth table. So we use a table called truth table. So to describe the relationship between the output and input of this black box, and to describe the relationship of this output and input of this particular black box, we use a table called truth table. Okay, so what is this truth table? This truth table is basically is a tabular form which shows the relationship between the input and outputs of a logical device. So the number of inputs may vary from 1 to many depending upon the device or the complexity of the circuits. This number may be dependent upon the circuit, and the number of outputs may also vary depending upon the circuit, right? So for different circuits, let's see some truth table. So let's say if we have one input circuit, if we have one input circuit and one output circuit, if we have a one input circuit as well as one input circuit. So let's say this is our circuit which has only one input and one output. This is one input and this is one output. Then the truth table for this particular circuit is given by A. So let's say our input is A and output is Y. So this is our input and this is our output, A comma Y. That's it. Okay, A may be 0, A may be 1. So depending upon the circuit inside this black box, our output will be generated. It may be 0 or it may be 1, or it may be 0 or it may be 1 when A is equal to 1. So this is how the truth table is going to give the relationship between the input and output. Okay, so this truth table is going to give the relationship between the input as well as output. So this is a case of one input circuit. And if we have a two input circuit, and two output circuit, then how it look like? So let's say this is a black box which consists of two inputs, A, B, and let's say two outputs, X comma Y. Okay, then our black box, then our truth table will look like this: A, B, X, Y. Okay, so what are all the possible cases of this A and B? It can be 0, 0, it can be 0, 1, it can be 1, 0, and it can be 1, 1. So for 0, 0, there may be some set of outputs according to the circuit which is present inside this black box. The outputs may be generated. Okay, according to the circuit which is present inside this black box, the outputs may be generated. It may be 0 or it may be 1, it may be 0 or it may be 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So according to the circuit which is present inside this black box, the outputs will be generated. So this is the truth table for two input circuit and two output circuit. If we have only one output and two inputs, then we will discard this and we will only keep this one output. So this is how we will draw the truth table, and we will describe the relationship between the input as well as output. So if a user or if someone sees this truth table, what he can understand, he will at an instance he can understand about the truth table. Okay, by seeing the truth table only he can understand the behavior of the circuit, how the circuit is behaving, how it is taking the inputs, how it is generating the outputs. By seeing the truth table itself, one can understand the behavior of a particular circuit. So that's how a truth table will help us to understand the behavior of a circuit, like how the circuit is analyzing the inputs and how the circuit is giving our outputs. So this is the use case of truth table. So this truth table we are going to use vigorously in our Boolean algebra and entire our digital. Okay, next. So let's see some basic Boolean operations which are needed. basic Boolean operations. So the basic Boolean operations which are present in this particular chapter are OR operation, NOT operation, and AND operation. Okay, OR operation, NOT operation, and AND operation. So these are the basic Boolean operations which are present. Now we will discuss them one by one. Okay. Now let's start with Boolean addition. Boolean addition, or it is also called as logical OR operation. Logical OR operation. Okay. Boolean addition, or it is also known as logical OR operation. So in this case of Boolean addition or logical OR operation, it is similar to normal addition, addition of normal algebra. So OR means logical addition operation. Okay, if you see a logical OR, it means a addition operation. It is also denoted by the symbol plus. Okay, so if you see anywhere logical OR, it is nothing but simple Boolean addition. For example, if we have a circuit, let's say this is our black box, and for this circuit we have an output Y and two inputs A comma B. Okay, if we have a circuit where the inputs are A comma B and our output is Y. Okay, so the behavior of the circuit is described using the Boolean algebra. Okay, the behavior of the circuit is described using Boolean algebra, like Y is equal to A plus B. Okay, so this is the behavior of the circuit which is represented in Boolean algebra. So this is how we are going to represent the behavior of the circuit using Boolean algebra. Why we are learning Boolean algebra? To represent the circuits in case of Boolean in ways of Boolean algebra. Okay, in the written form we are going to represent the particular circuits. So this is basically logical OR operation. So what this Boolean expression is representing us, or what it is telling us, that is output is nothing but in sum of two inputs A and B. That is addition of two inputs, or Boolean OR of two inputs A and B. So this is how the Boolean algebra is used, will help us. Okay, so it will basically explain the behavior of the circuit. Okay, yeah. So this is Y is equal to output is nothing but A plus B. So how to write the truth table for this? In the previous slide only we have learned how to write the truth table. So let us see how to write the truth table for this logical OR operation. So basically in all the truth tables, inputs are written first. Okay, remember this, in truth tables inputs are written first followed by the outputs. Okay, inputs are written first followed by the outputs. So this is the input followed by the output. So inputs are written first followed by the outputs. So what are the inputs for our particular design? The inputs are A comma B. A comma B. So for our design, the inputs are A comma B. And what is the output? The output is Y. Okay. So the inputs for our design are A comma B and the output is Y. I'll write it here, which is nothing but A plus B. Okay. So the inputs for our design are A comma B and output is Y, which is nothing but A plus B. So what are all the combinations of A and B? It can be 0, 0, it can be 0, 1, it can be 1, 0, and it can be 1. So this is how we are going to write our truth table. And what is the output? Y is equal to A plus B. 0 plus 0 is nothing but 0, and 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0. So in the logical OR, there is no carry. Okay, so if any of the two inputs are 0, output is 0, and if any of the two inputs is 1, the output is 1. That's it. If the two inputs are 1, the output is 0. This is logical OR. Okay, this is not normal addition where we have a carry. Here we don't have any carries. Okay, this is logical OR operation. So by seeing the truth table itself, you can describe about the circuit. That is, the circuit is adding the two inputs, Y is equal to A plus B, and if you provide two inputs such as 0, 0, the output will be 0, and if you provide two inputs 1 and 0, 1, output will be 1. So like this truth table depicts the behavior of a circuit, of a logical circuit. So this is how the truth table will help us to depict the behavior of a circuit. Okay, next comes the Boolean multiplication. Boolean multiplication. So how it is represented? Boolean multiplication is nothing but logical AND. Boolean multiplication is nothing but logical AND. What is Boolean addition? It is nothing but logical OR. Okay, Boolean addition is logical OR and Boolean multiplication is logical AND. Okay, Boolean multiplication is logical AND. So how it is represented? Basically, this Boolean multiplication is represented by a operator called dot. Okay, so we are going to represent this logical AND using this operator, dot operator. For example, again we will consider our circuit or a black box. If you see, this is our black box. We don't know what is inside this black box, and we have two inputs A and B and output Y. Okay, so to represent this Boolean multiplication using the Boolean expression, how we are going to represent Y is equal to A dot B. Okay, so this Boolean expression is depicting the behavior of this particular circuit. Okay, this is nothing but Boolean expression. This Boolean expression is telling how the circuit is behaving, right? So Y is equal to A dot B, that is multiplication, Boolean multiplication of A and B. So how to write the truth table for this particular Boolean expression? We will write the input first, followed by the output. Okay, input and output. What are the inputs? We have A and B. A, B. And what is the output? We have Y. Okay. So what are all the possible combinations of A and B? 0, 0, 0, 1, 1, 0, 1, 1. So 0 dot 0, that is 0 multiplied by 0 is 0. And 0 multiplied by 1 is 0. 1 multiplied by 0 is 0. 1 multiplied by 1 is 1. That's it. This is the Boolean multiplication, or it is also known as logical AND. So this is how we are going to perform Boolean multiplication or logical AND. Okay. Now, next coming to logical NOT. Logical NOT. So NOT is the simplest of these three basic of Boolean algebra. It is also known as inversion, and it is also known as complement. Okay, it is known with these two names, inversion, or it is also known as complement. So the NOT operation is indicated by bar over the variable. So if we have an input A, then NOT of A is nothing but A bar. So this is represented as A bar. Okay, so if A is a variable, then NOT of A is represented as A bar. Let's say if we have a design again, we'll consider our black box which has one input A and our output Y. So this what is the behavior of the circuit is nothing but our output is NOT of A. Okay, so this we want to represent it in Boolean algebra. So how to represent it in Boolean algebra? We will represent it in Boolean algebra using the bar operator Y is equal, or the complement operator Y is equal to A bar. Okay, so we are representing our circuit behavior in terms of Boolean algebra like this. Y is equal to A bar. Okay, Y is equal to A bar. How to write the truth table? We'll write the truth table like this: inputs followed by outputs. So this is our input. How many possible cases of inputs are present? Two possible cases. Input can be 0 or input can be 1. So if the input is 0, then the output is 1. And if the input is 1, output is 0. So this is nothing but the complement operation or bar operation. Okay, complement operation, or it is also known as logical NOT operation. Okay, so if the input is 0, output is 1, output is 1, if the input is 1, output is 0. So this is how we are going to represent our logical NOT operation in case of Boolean expressions. So is it clear up to here? So if you are having any doubts or queries, you can post it in the chat. Okay, and if you're liking this session, please like and share with your co-VLSI friends, and do subscribe to our channel all about VLSI so that we can bring a similar kind of content. Okay, yeah. Now let's see some theorems in our Boolean algebra. Okay. Theorems in Boolean algebra. Okay, so basically we use these theorems to solve the Boolean expressions. Okay, so we'll see these theorems one by one. So first theorem is called complements law. Complementation law. And second one is called, and so we will discuss one by one. So first we will discuss about this complementation law. So the term complement implies to invert, that is change ones to 0 and zeros to 1. What is meant by complement? Complement is nothing but changing 1 to 0 and 0 to 1. This is complementation. That is, we are going to change the variable from 1 to 0 or 0 to 1. So what is complement of 0? Complement of 0 is nothing but 1. And what is complement of 1? That is nothing but 0. So this can be represented as 0 bar, which is equal to 1, and 1 bar, which is equal to 0. Okay. So if we have a variable a, which value is 0, then what is the value of a bar? Then what is the value of a bar? Anyone? Any answer? Then the value of a bar is nothing but it is equal to 1. Okay. And if we have a variable a which stores the value of 1, then what is the value of a bar? Which is equal to 0. So this is the complementation law. So 0 changes to 1 and 1 changes to 0. Next, if a variable stores a value of 0, then what is the double complement or double bar? A double bar, which is equal to 0. Okay. So from this we can conclude that a double bar, which is equal to a. So this is the double complementation, does not change the function. So these are the basic complementation laws which are present in Boolean algebra. Is this clear? Now let us discuss about AND laws. So we have one more law which is called as AND law. What is this AND law? So in this AND law, the 4 AND laws, so we have 4 AND laws. First one is null law. So if we have a variable a, if we multiply with 0, the output will be 0. This is null law. A dot 0 is equal to 0. And we have one more law which is called as identity law. Where if we multiply any variable with 1, we get the same variable. That is a dot 1 is equal to a. If we multiply any variable, then we will get the same variable. Okay. Next we have, if we multiply two identical variables, let's say a dot a or let's say b dot b, we will get the same variable. Okay. A dot a is equal to a or b dot b is equal to b. Okay. Now, if we multiply a variable with its complement, then the output will be equal to 0. So if we multiply any variable with its complement, then the output will be equal to 0. You can also see this, b dot b bar is equal to 0. If you multiply any variable with its complement, the output will be 0. Whereas if you multiply the same variable, okay, 2 times, the output will be a itself. B dot b is equal to b, a dot a is equal to a. Okay, so this is AND law. So these are the AND laws which are present. One is null law. If you multiply any variable with 0, the output is 0. And if you multiply any variable with 1, the output is the same variable. And if you multiply two variables, okay, the output is the same variable. And if you multiply any variable with its complement, then the output is equal to 0. If you multiply any variable with its complement, then the output will be equal to 0. Okay, next. Next, discuss about OR law. OR laws. Same, we have four laws. First one is null law. Here, in the case of null law, if we add any variable with 0, the output will be the variable itself. A plus 0 is equal to A. Next, identity law. A plus 1. If we add any variable with 1, then the answer is 1, not A. It is 1. Okay. So if you add any variable with 1, then the answer is 1 itself. Okay. A plus 1 is equal to 1, not A. Okay. So in the identity law, if A is added with 1, the output will be equal to 1 itself. Okay. Next, if a variable is added with itself, then the answer is the variable itself. Okay, that is A plus A is equal to A, or B plus B, which is equal to B itself. Same as in multiplication law or AND law, A dot A is equal to A. Similarly, A plus A is equal to A. But if you add A plus 1, the answer will be 1, whereas A dot 1 will be equal to A. Okay, remember the difference. Now, if we add a variable with its complement, the answer will be equal to 1. Similar to A dot A bar, which is equal to 1. Here also A plus A bar is equal to 1. Okay, I hope this is clear. So these are the OR laws which are present. Okay. Next, we have one more law which is called as commutative law. We have a law called commutative law. So basically this commutative law tells that A plus B is equal to B plus A, or A dot B is equal to B dot A. So this is the commutative law. The order of variables in OR and AND operation is not important. Okay, the order of operations in OR and AND are not important. Here the order is not at all important in the case of commutative law. Okay, next let's discuss associative law. So in the case of associative law, the grouping of variables in AND or OR expressions does not affect the result. For example, A plus B plus C, which is equal to A plus B plus C. Here we are basically changing the grouping. Here B plus C are grouped, and which is also equivalent to A plus B grouping. Okay, so the order of grouping is not affected in the case of associative law. So the associative law states that the order of grouping is not affected. Okay, you can group anywhere. A plus B plus C, which is equal to A plus B plus C. Okay, or you can also do A dot B dot C, which is equal to A dot B dot C. This is also possible. This is what associative law states. Next comes the distributive law. So these are basically used when we are going to solve the Boolean algebra expressions. So these are very helpful actually. Okay. Now we have distributive law, which states that basically distributive law allows factoring or multiplying out expressions. There are two distributive laws actually. So which is the first distributive law is A into B plus C, which is equal to AB plus AC. Next, second one is very important actually. This we will encounter in many problems actually. When we are solving problems, we will encounter this type of format, which is nothing but A plus BC, which is nothing but A plus B into A plus C. So you can write A plus BC, which is as A plus B into A plus C. So this is distributive law. A plus BC, which is equal to A plus B into A plus C. So this is distributive law. Now, using this distributive law, we can come to a conclusion of another law, which is called as redundant literal law. rule. Okay, redundant literal rule. So using the distributive law only, we can come to a conclusion of this. Let's say if we have a plus a bar b. Okay, so if we have an expression called a plus a bar b. Okay, so how to solve this expression? According to the distributive law, it can be written as a plus a bar into a plus b. Okay, so according to the distributive law, we can write this particular expression as a plus a bar into a plus b. Okay, what is a plus a bar? In the OR operations only we have seen a plus a bar is nothing but 1 and a plus b is remaining. So answer is a plus b. So what is the redundant term we are removing? Which is nothing but a bar. Okay, so this is the redundant literal rule. Okay, so we can remove the redundant literal which is present here. Okay, so by using the distributive law, we can able to remove the particular redundant literal. Okay, now we have one more law called as idempotent law, which states that, so basically here, if we multiply the same variable for, let's say, n times, the answer will be equal to a itself. And if we add this variable for n times, the answer is a itself. So this is what idempotent law. Okay. Now we have one more law called absorption laws, but that is not very important. We will go to we'll discuss about De Morgan's theorem, which is a very important, which is a heart of our Boolean algebra. De Morgan's theorem. What is this De Morgan's theorem is about? Okay, so basically De Morgan's theorem states that if we have two variables, let's say a and b, then a plus b the whole bar, which is equal to a bar dot b bar. Okay, a plus b the whole bar, which is equal to a bar dot b bar. And if we have a b the whole bar, then this is equal to a bar plus b bar. So this is De Morgan's law, which is a very important theorem. Okay, this is widely used in our Boolean algebra. Okay, De Morgan's law states that a plus b the whole bar, which is equal to a bar dot b bar, and a b the whole bar, which is equal to a bar plus b bar. So this is all about today's session. We have started with basic Boolean multiplication, addition, basic terminologies like truth table, everything we have discussed, logic levels we have discussed, and we have started with the discussion of laws, Boolean algebra laws, which are very important for our calculation of Boolean algebra for solving the Boolean algebra expressions. Okay, yeah. So that's all for this session. So if you are having any doubts or queries, you can ask me in the chat, or else we can end this session. Okay. So please do like, share, and subscribe to our YouTube channel all about VLSI. Okay. Yeah. Thank you.